Let's see another example of the transformation method. And this example concerns order statistic. So what is order statistic? Hopefully you have learned that from 410, but in case you haven't, or if you have forgotten about that, here's the definition. Suppose that we have y1, y2, all the way up to ym, which are IID random samples from a distribution fy. Then the kth order statistic is a statistic, and it is the kth smallest value in these samples, so y1 up to ym. And here are some well-known and important examples. The minimum of all of these samples is a order statistic, and that's the case where k is equal to 1. So that's the smallest value out of all of these samples. And then the maximum is another order statistic. So that's the case where k is equal to m. So that's the larger value among all of these samples. So in classes like 410 or 510, if you have introduced the order statistic concept, then you might have learned in one of these courses how to derive the CDF or the PDF of the kth order statistic. And let's denote that by y parentheses k. So that's the kth smallest value out of all of the y draws. I have provided the CDF and the PDF's general forms over here. And you can apply these forms and you can derive these and you can apply these formulas to find the specific distribution of a order statistic when you know the formula or the distribution of y. However, let's not try to do it over here. You can see that it can be really computationally laborsome. Our question here is, can we draw random samples of the kth order statistic, yk, without deriving the PDF or the CDF for yk? Well, the answer is yes. And we'll see an example of that. Let's say we want to draw 1,000 samples of the kth. So here k is equal to 50. The 50th order statistic of y1 all the way up to y100, which are IID random samples from the normal distribution with mean 5 and standard deviation of 2. In other words, we have these 100 samples from this normal distribution, and we want to find we want to obtain samples of the 50th smallest value out of all of these random samples. So let's notice something here. So why can we apply the transformation method? Note that y50, which is the 50th order statistic of the 100 draws, is a function of y1 all the way up to y100. Let's denote y50 by x for convenience. And because x is a function of the y's, this means that we can first draw the y's, which are easier to sample from, and then use some kind of transformation to find the x's. And let's use the transformation method to draw the x's, the order statistics in this case. Here's the code that implements this, and it might not be very straightforward when you first look at it. We first create a random matrix instead of random vector here. So this is going to be a matrix where each entry is a normal sample with mean 5 and standard deviation of 2. And we have a total of 1,000 rows and 100 columns. So you can see that for this matrix, for each of the 1,000 rows, the row has 100 IID normal 5-2 samples. So each row can be seen as one replication of y1 all the way up to y100 following this distribution. Now, let's apply the transformation to each of the rows. We first define a function h, which takes input of a vector of y's, in this case 100 entries, and then what it returns is the 25th. Sorry, it should be 50 here. Let me modify this. So this h function, when we want the 50th order statistic, returns the 50th smallest value of the y vector, our input. And notice that we did this by using the sort function. So the sort function, without giving any other additional arguments, allow us to sort a vector from the smallest value to the largest. And we take the 50th entry to it, so it's the 50th smallest value out of this sorted vector of y's. So that's what the h function does. Now, let's try to apply the transformations and get our x's, in other words, our y50s. In this case, we can use a function called apply. The apply function does the following. So it's going to apply a function to an array, so something like a matrix or a three-dimensional array, and then it's going to apply the function, say our h function, to either each row, each column, or some other combinations or margins of this array, or in this case, our matrix. So in this case, let's do apply y, where y is the matrix we first created with 1,000 rows and 100 columns. Each row is one replication of this. We say margin equals to 1, which means that we're going to apply the function to each row. If you want to apply some function to each column, you say margin equals 2. So what function do we want to apply to each row of the y matrix? We want to apply the h function, where we do the transformation between the 100 y's and obtain the x's. So let's say our x values is going to be the result of applying the h function to each row of the matrix y we first created. And the resulting x will be a length 1000 vector. And for each of the entries, it will be the output of applying the h function to the corresponding row of the y matrix. So we know that ideally or theoretically, the x's should be distributed the same way as the 50th order statistic of the y samples. So my code over here actually implemented 25, so the results will be for 25. Let's take a look at what it looks like. So on this histogram over here, I have plotted the empirical distribution of our sampled x's. So in this case, it's the 25th order statistic. You can change the value back to 50, and that will give you the empirical distribution of the 50th order statistic. So this is how I actually screwed up the code on the earlier page. As an optional exercise, you can try to play with the value of k. Let's say for the example, we wanted to try k equals 50. Let's say try some other possible k values, such as 1, which will give you the first order statistic. In other words, the minimum of the 100 draws. 25, 50, 75, and 100. And 100 will give you the maximum out of all 100 draws. And then for each of these order statistics with different values of k's, you can see how the distribution of x equals y parentheses k, the kth order statistic, changes by altering these values. So The code that we have just seen implements the method to obtain draws of the order statistic. Let's consider a more general case where x equals a transformation h of y is any statistic of I random samples y1 all the way up to ym. Not only just order statistic. Order statistic is one possible type of statistic. Let's recall that a statistic, by its definition, is a function of random variables. So it's a function of the y's. So it itself is also a random variable. Then the transformation method can be really useful for drawing the x's, which is the value of the statistic, or samples of the statistic, under some kind of null hypothesis. For example, each of the yi's under the null hypothesis follows some distribution f0. This will allow us to numerically approximate the null distribution of our statistic x. So this can be the sample mean, the sample standard deviation, the maximum, some other order statistic, or in general, any kind of statistic of our random samples. And we can numerically approximate the null distribution of the statistic without deriving its distribution, which is quite nice. And this can be really helpful when we want to approximate and when we want to do hypothesis testing using numerical methods, because in that case, we want the null distribution of a statistic. We will talk more about this next week.